Good afternoon everyone. Today we are going to see fuzzy logic control part 2. In that we are going to see about fuzzy PI PD controller coming under Mamdani controllers, and then we are going to see about TS fuzzy controller. Now the outline is, as I said, first we are going to see fuzzy PI and PD controllers that falls under fuzzy Mamdani controller. Then we are going to see Takagi-Sugeno fuzzy control, that is TS fuzzy control. First let us start with the fuzzy PI controller. You know that the classical PI controller is given by an expression in continuous form u of t equal to kp e of t plus ki integral 0 to t e of tau d tau, where kp is the proportional gain, ki is the integral gain, and e of t is the error, and u of t is the control signal. The discrete version of the above PI controller can be written as u of k equal to kp multiplied by e of k minus 1 plus ki multiplied by e of k minus 1 plus e of k minus 2, and it continues, multiplied by delta t. Thus we can say that from the above two equations we can say u of k minus 1 is given by an expression which is kp into e of k minus e of k minus 1 plus ki into e of k into delta t, where delta t is the sampling time, and we can say that u of k is given by an expression u of k minus 1 plus delta u of k, where delta u of k is a function of error and change in error, and that is given by u of k minus u of k minus 1, and it is a function of, as I said, E, change in error, and higher order forms. Now coming to the fuzzy PI controller, the fuzzy controller will have the control structure given by u of k equal to u of k minus 1 plus delta u of k, and using the fuzzy rule base delta u is obtained, which is nothing but an incremental control action which is a function of error and change in error, E and delta E respectively. Now looking at the general characteristics of a PI controller response, the rule base is formed in fuzzy PI controller. Now let us say that this is the response of the PI controller, then we can say with some nomenclatures, PL stands for positive large, PM stands for positive medium, and PS stands for positive small, and ZE stands for 0, and NS stands for negative small, and this is basically having the response to the steady state desired output, which is here 1. So the error is given by yd minus y, where yd is the desired steady state output and y is the actual output, and from this response we can derive the rules as such with E and E dot, which is nothing but precisely E. Let us take any one. If E, if the error is 0 and error dot change in error is also 0, then the control action, which is an incremental control action delta u, is 0. Let us say that if the error is positive small and change in error is 0, then your change in control action, the incremental control action, is positive small. Likewise, if we say if the error is positive medium and the error change in error is positive medium again, then you have to have your delta u coming out to be positive large. Let us say that if the error is positive small and your change in error is negative small, then what will be your delta change? It is 0, because you have your change in error is negative sign, negative small. Okay, so it is going to get reduced slowly. So we are here because of the error positive small, and it has to reach here and it has to reach here to the desired value, with your change in error also reducing. That means your actual value as the time goes on, it is also decreasing towards the desired value. So, in that case your delta u, you do not have to give any delta u, that is why in that case it is 0. Okay, so, in this way for fuzzy PI controller, from the response of the controller we can have our rules formed or rules developed, so that they form the rule base. So, this is called intuition based rule base. Based on intuitions we can have our rules developed, rule 1, rule 2, rule 3, rule 3, rule 4, rule 5, rule 7, 8, 9, 10 accordingly. Now, let us move on to fuzzy PD controller. A classical PD controller is given by the control law u of t equal to kp into error, it is u of k, plus kd into e of k minus e of k minus 1 upon delta t. Thus, the control action u is a function of e of k and change in error. So, if you want to have the rules, we can have the rules based on 3 linguistic variables e, e dot and u, where u is the output linguistic variable and e, e dot are input linguistic variables. Now, the fuzzy PD controller can also be expressed as a function of e of k and delta e of k to form the rule base, as I told. Now, the rule base, let us take an example, that is say 2-link Cartesian position control, 2-link robots Cartesian control, like you need to control the position of the end effector. I need to go here. So, this is your x desired, this is your x actual. Now, that is my goal. So, if we are going to derive the rules for this control objective to have the 2-link planar robot to reach a desired position in the Cartesian space, we are having here E change in error, and change in error as 2 input linguistic variables for the fuzzy controller, and U being the joint torque, controller being the joint torque, what will happen in this case? So, rule 1 can be, if E is positive high and delta E is positive high, then the joint torque is positive high, because if the error is too large, then your current value or actual x actual is very less to reach the desired value. And also your change in error is positive high, which implies that at every instant we have our actual value not moving towards the desired value of the robotic system. The robot has to reach xd. So, change in error keep on increasing, which is positive high, which implies that the current robot end effector is not moving towards the desired value xd. So, joint torque must be positive high to bring it to the desired value xd. That is what given in rule 1. Likewise, let us move on to rule 2. If the error is positive low, that means you are close to the desired point in the Cartesian space, and your change in error delta E is positive low, then the joint torque is also positive low because of the closeness to the desired position in the Cartesian space. Your change in error is also positive low, That means at every instant the actual position of the robot is moving towards the desired position, and hence the joint torque, that is the control signal given to the robotic system, that is tau 1 tau 2 given to the robotic system, is also low. Now let us see an example with a single link manipulator of PD controller, implementation of a PD controller towards a single link manipulator control. Let the dynamic model of a single link manipulator is given by tau equal to theta double dot plus 10 multiplied by sin theta, where theta is a joint angle from the vertical position and tau is the joint torque. Now considering x1 is theta and x2 is theta dot as the state variables, the control input u as tau, we can have the state space model of this single link manipulator as x1 dot equal to x2 and x2 dot equal to minus 10 times sine of x1 plus joint torque u. So upon doing the state space control of it using a simple PD controller of the state space model of the single link manipulator, we obtain this joint angular result, where we can see the input joint torque is obtained with saturating, like, or we are having a maximum cut short of that, like we are forcefully suppressing that if it is more than 20 and less than 20, we are making it to be within that limit, hard limiting the control input to this system. With this hard limitation of the control signal to this system, we get the response as shown in the slide here, which is we have the settlement of the system that is coming around 2.5 seconds, or precisely you can say 3 seconds, and then we have the time history of the error and derivative of the error, where you can say that there is a steady state error for the joint angular value, and hence we can see that the error is not becoming 0 in this case. For a desired value, it is not converging to that. Then we need to tune the Kp and Kd control gain parameters to obtain the steady state error 0. Now there exists some steady state error in this situation. Now let us design a PD controller for this same problem. So we need to form the rules. Let us say that the fuzzy sets associated with the input variable or fuzzy linguistic variable be negative, positive and 0 for the fuzzy linguistic variable E. Likewise, the another fuzzy input linguistic variable has the fuzzy subsets. These are the subsets, not the sets, these are subsets N, P, Z. So that will give you the output based on your value of fuzzy linguistic variable 1, that is E, and fuzzy linguistic variable E dot. Based on that, we are going to have E being negative, positive, 0. Now there are two linguistic input fuzzy variables with the fuzzy subsets being 3. So the number of rules that is going to be here is R equal to Q power n. The two state variables with the Q being 1, 2, 3. So 3 power 2 equal to 9 rules going to be formed with this combination of negative, positive, 0 for E and E dot. So we form those 9 rules so that they are going to be the rule base. Rule 1, say when E is negative, E dot is positive, accordingly U is 0. Likewise, when error is positive, error dot is positive 2, then we have your u, that is control signal, to be negative. Likewise, we form 3 power 2, that is 9 total rules for this control problem. And then once we form these rules, then we will be finding the membership function values for the corresponding rules for this membership function value and for this input membership function value, that we will be doing the AND operation to give the consequent membership function value. Likewise, we do all. Once we complete all, then we do get the output distribution by maximizing the consequence. When we do the maximization of all the consequence of all the rules, then we get the output distribution. From the output distribution, we can get the crisp value upon defuzzification, which we can use either center of gravity approach or weighted average approach to get the crisp value. And that crisp value is going to be your u, that is control signal, that is going to be given to the single link manipulator. So, the simulation that we have done in this problem will be as such. For each instant, you have the output, crisp output value obtained from the output distribution is as such. Because this is a regulation problem, your control signal u converges to 0, as you can see, once the complete iteration gets over. Once your complete iteration gets over, your crisp output value is 0, because this is a regulation problem. And this is the results that we obtained from this simulation study of a single link manipulator upon fuzzy PD controller. And finally, we have our joint angular trajectory, which means that convergence of the joint angle of the single link manipulator. We started with some value around say 23 degrees and it get converged to 0 degree, and hence it is a regulation problem. You start from some non-zero value and make it get converged to 0 value, and hence to make this, your control signal in this problem converges to 0 as well. Now, let us talk about Lyapunov-based approach. Here, it implies very explicitly that Lyapunov-based approach, which means that we are going to use Lyapunov function candidate, which is a positive definite function candidate, scalar function candidate, which will be utilized to develop the rules. Because so far we have seen the rules are developed based on intuition, whereas here we have the Lyapunov stability analysis in order to form the rules. Let us have an example, simple example given by the linear model x dot equal to ax plus bu, where x dot is given by this 3 cross 3 matrix multiplied by x plus 3 cross 1 vector multiplied by u, where A is the matrix 3 cross 3 matrix given by 0 1 0 0 0 1 and 0 0 0, and the B vector is given by 0 0 1. Here the inputs are the state variables are x1 x2 x3. The fuzzy sets for these state variables are, that is the fuzzy subsets for these inputs are positive, 0 and negative for each of these, x1 positive, 0 and negative, likewise for x2 positive, 0 and negative. So, for x3 again it is positive, 0 and negative. So, how many rules we are going to have? Definitely it is 3 power 3, 3 state variables and 3 subsets associated with each state variable. So, 3 power 3, it is 27 rules going to form the rule base, and the fuzzy subset for output u are large positive, positive, 0, negative and large negative. Now from the fuzzy controller we are extracting the control input u by giving x1, x2, x3 the state variables as input to the fuzzy controller. Now the rule base is going to be formed by having 27 rules, out of which we are going to see few rules because of time brevity. Using the Lyapunov function we are forming these rules. Let the Lyapunov function candidate be v equal to half x transpose x, where x is a vector of 3 elements x1, x2, x3. Expanding that, half x transpose multiplied by x will get half x1 square plus x2 square plus x3 square. So this is v. Now we want v dot, the time derivative of the Lyapunov function candidate, to be negative definite. So we take the time derivative of it, which is x v dot equal to x1 dot plus x2 dot plus x3 dot. So from the state space model, x3 dot is nothing but u. So we have x1 dot, x2 dot, x3 dot in the left hand side. From that, expanding that, we will have x3 dot equal to the control input u. Thus it is given expanded as v dot equal to x1 x2 plus x2 x3 plus x3 into u. So the objective of this controller is to find a control input u such that the system is stable around x equal to 0, because x equal to 0 is the equilibrium point. And from the Lyapunov theory we know that v dot should be less than 0, that is negative definite. Now using this we will try forming the rule base for the controller. First let us consider all the 3 state variables x1, x2, x3 are positive. To make v dot negative, we analyze the following form of the expression for v dot. So v dot be positive plus positive plus positive into u. Therefore u should be large negative, because we have taken x1, x2, x3, all the 3 state variables being positive. So the first term will be x1, x2, x2, x3, so positive positive, and the third term will be x3 and x3 dot. So x3 dot is u, so positive into u. In that case u should be large negative in order to have v dot be negative. Now accordingly the rule statement is, if x1 is positive p and x2 is positive p and x3 is positive p, then u is Ln, which is large negative. That is how we are done with the rule 1. Similarly, consider the case x1 equal to 0, x2 greater than 0 and x3 less than 0. So in that case v dot is going to be 0 plus negative into u. So in that case u is positive or 0 to make v dot negative. Therefore the rule is, if x1 is 0 and x2 is negative and x3 is negative, then u is positive or 0. Likewise for different combination of the inputs we get a total of 27 rules, and this type of Lyapunov-based stability oriented fuzzy controller will be helpful in our percutaneous needling intervention towards minimal invasive surgery, where the control input is the needle spinning velocity and the insertion velocity. Now let us move on to the second portion of today's lecture, which is TS fuzzy control. In 1985, Takagi and Sugeno proposed a powerful fuzzy model representation which states that if a non-linear system is represented by a cluster of locally defined linear systems, then the systematic understanding of the non-linear system becomes stronger, as we know the linear systems already. The TES fuzzy control has this flow chart, which is quite similar to Mamdani controller. it is this one, the arrow mark is wrong. So, from the plant we get the information through the sensor, which is a crisp value converted to fuzzy through fuzzification, and the fuzzification or the fuzzy value enters the fuzzy inference mechanism, and then fuzzy inference mechanism which does the rule evaluation, from which we get the fuzzy value that gets converted into crisp value by defuzzification, where center of gravity or weighted average approach is utilized, and that crisp value goes to the actuator for which the system is actuated. Now, in the fuzzy inference mechanism, the fuzzy rule base with output state variables represented by an expression or a model. That is the difference, because straight away we will not be forming the output variable. The fuzzy output linguistic variable is obtained through an expression or a model. Precisely here we are going to see an example where we are going to use a linear model in order to obtain the fuzzy output variable. Considering a general continuous nonlinear dynamical system described by x dot equal to f of x comma u, where x and u are the n and m dimensional state and input vectors respectively. On fuzzy merging of equivalent linear systems in different operating domains using the TS fuzzy modeling, the above non-linear system can be effectively modeled. I repeat, by fuzzy merging of equivalent linear systems in different operating domains using the TS fuzzy model, the above non-linear system can be effectively modeled. In general, a TS fuzzy model is composed of n rules, where the ith rule is given by the following form. Rule I: if x1 is t1i, where I corresponds to this rule I, and x2 is t2i, accordingly it goes up to xn is tni, then x dot equal to aix plus biu, where x is an n dimensional state vector and you have your I varying for this system towards S, which means S number of rules, and the number of rules is given by q power n, because each rule represents a fuzzy region in the state space of n dimension, thus representing total number of rules equal to q power n, that is the number of fuzzy regions if each state is fuzzified into q fuzzy zones. In continuation of TS fuzzy control, by providing the current state vector x and an input vector u, the TS fuzzy model representation of the system dynamics is given by x dot equal to 1 by summation over I equal to 1 to s mu I multiplied by summation of I equal to 1 to s mu I of ai xi plus biu, where mu I is given by the product over j equal to 1 to n mu I j of xj, where the mu I j is the membership function value of the fuzzy term tji. Upon representing the normalized membership function value associated with the ith value by beta I equal to mu I upon summation over I equal to 1 to s mu I, then in the discrete domain the TS fuzzy model representation of a discrete time nonlinear system is given by an expression x of k plus 1 equal to summation I equal to 1 to s beta I ai x of k. This is the final expression to get the next state variable given the current state variable. Now take an example to understand this TS fuzzy model. Let us consider a single link manipulator whose dynamics is given by x1 dot equal to x2, x2 dot equal to minus g by L sin of x1 plus 1 by ml square into tau, that is the tau is the control input u, where x1 equal to theta is the angle of the manipulator from the vertical axis and x2 equal to theta dot is the angular velocity of the manipulator, and tau is the control signal, precisely the control torque for this manipulator. The parameters are mass m equal to 1 kilogram, length L equal to 1 meter, and g acceleration due to gravity is 10 meter per second square. Now the question asked here is derive any two rules that describe the TS fuzzy model of the above system. The solution here is let the fuzzy subset of x be PL, PS, ZE, NS, NL obtained as a combination to a set x1. Precisely the fuzzy set of variable x1 be capital X1, which is given by a set of these subsets or elements. Accordingly, for x2 it is capital X2 equal to PL, PS, ZE, NS, NL, positive large, positive small, 0, negative small, negative large. These are the 5 subsets associated to the fuzzy set x2 as well as x1. So, by seeing that you can say that two state variables x1 and x2 and the fuzzy subsets associated with each state variable is 5. So, it is q power n as the number of rules. So, 5 power 2, 25 rules, total rules. Now, 2 of these rules only asked as the question. If x1 is positive large and x2 is 0, then x dot is given by a1 x plus b1 tau. x1 is basically the joint angle variation, is positive large, the is the x minus x, and this is basically the single link manipulator, and you can have positive angle, this is a theta, so it comes here. So, positive large, let us say 85 degree being x1 and x2 your angular velocity being 0. So, for this system you have A and B matrices coming out to be 0 1 minus g by L sin of x1 0, B equal to 0 1 by ml square. Substituting the value of g, L and m, we get A equal to 0 1 minus 10 times sin of x1 0 and B matrix is 0 1. Now, coming to the linearized form of A given by A1 equal to the Jacobian matrix, which is given by dou f1 by dou x1, dou f1 by dou x2, and the second row is dou f2 by dou x1 and dou f2 by dou x2, the partial derivative of this matrix, that is say A1, that is given now upon linearization, it is given as 0 1 and minus 10 cos of x1 0, 0 1 minus 0.87 and 0, and B1 is 0 1, because here x1 is 85 degrees we are substituting, and accordingly we get minus 0.87 0 in the second row. Therefore, the rule 1 becomes if x1 of t is positive large and x2 of t is 0, then we have x dot equal to ax plus bu, where a is this a1, b is this. Likewise, rule 2, if x1 is positive small and x2 is 0, then x dot equal to a2x plus b2 tau, where a2 is the linearized form of a with operating point given by x1, which is positive small, because x1 is positive small, say 10 degree, and x2 is 0 again, so it is 0. So, accordingly we will have the rule coming out to be x dot equal to a and b are given by 0 1 minus 9.8 0 and B matrix is 0 1, which is obtained by substituting the value of positive small. That is how we finished our TS fuzzy model understanding. Now, coming to the conclusion of this lecture, we have seen today fuzzy PI, fuzzy PD and Lyapunov function based formation of rules. Once the rule base is ready, then we can proceed further using defuzzification and get the crisp value, and we can go for controlling the plant. Then we have seen TS fuzzy control theory along with a simple single link manipulator example. In the next class, we will be seeing fuzzy C-means clustering. Thank you very much for your time.